This video is about area and distance using calculus. For our notes, we'll begin with a visual example where we want to find the area bound by f of x and then several other things as well. X equals a, x equals b, and the x-axis. So we have a quadrant 1 graph drawn here with a curve just kind of swooping through this quadrant, and that's labeled as y equals f of x. That's our function. It's just an example representation function. But then these other items by which we're going to be bound here would be not only that curve, but also this x equals a, which would be like a vertical line right at x equals a. And then for x equals b, we'll move down the x-axis to the right further and just mark a place for b there, which means, of course, vertically speaking, there'd be a vertical line there. And what this means is that we're bound by all these things: the curve, those two vertical lines, and the x-axis, which means we're stuck in this shape in the middle. Now, the reason that this is a significant problem is because that's not a familiar geometric shape, which, we already have a formula for to compute the area. We're used to areas of rectangles, triangles, even other more complex geometric shapes that have nice predictable formulas, but something like this is fairly irregular and there's no set formula for it. So we rely on some concepts of calculus in order to approximate this area and even ultimately find it exactly. And here's how we can do this. I just mentioned that we do know the area of nice convenient shapes like a rectangle or a triangle. We're going to rely here on the rectangle, so let me be a little more careful with my picture and redraw it in a couple key ways. I'm going to take this interval from A to B that we now have on the x-axis, and I'm going to just chop it up into a few pieces. So maybe I'll cut it in half and then even into fourths. It doesn't really matter at this point. I'm just giving it some breaks or chops in it. And what if for one of those intervals, so let's start way at the left side where A is, right? X equals A was that left vertical boundary. What if we made a rectangle such that the base of the rectangle was from A to the first tick mark we've drawn in this first interval here? Now we have 1, 2, 3, 4 different intervals based on those little divisions I put on the axis here, right? But if the first space from A to the first tick mark is the base of a rectangle, and then I were to raise the rectangle so that the right side of that interval, which I don't have a label for, but it's the first tick mark after A, if I raise it so that the right side of that interval actually hits the function, we'll just draw it until there. So let's suppose that the right side of this interval, this first interval after A, raises until it hits the function, and then from where that happens, we move over to draw the top of the rectangle and then also draw it down the left side, so that now we have a rectangle whose base is from A to the first tick mark, and notice whose height really kind of depends on the function value at this first tick mark here. That's the height of this rectangle. Now I'm just kind of picking it that way for a reason. You'll see why in a minute, but let's do that, and notice that that rectangle wouldn't be a really good estimate for the area under the curve in that interval. In fact, it'd be a little high because there's some extra area. If I were to compute the area of this rectangle, it'd be too high due to the part of the rectangle that's actually above this curve. It's beyond the boundary that we're specifying in this problem. Now, what if we moved on to the second interval and did the same thing? So the base is the width of that interval, and then let's also recognize that if I go to the right side of the second interval and raise that up until I hit the function, and then use that for the height of a rectangle, this rectangle, the second one, would also be an overestimate. Okay, fine, but at least I'm getting a rectangle that's trying to represent my region. Now, if I keep this going, and keep the theme of using overestimates, so in the third interval, again, I'll use the right side, which when I raise it up to the function and then go across to make a rectangle, we'll still see, or still be above the the curve. In other words, it's too big. The rectangle area is actually too much. Notice in this last interval, this fourth one, if I did the same thing, which is use the right side interval, which would now be at B, our right boundary. If I raise up from B and until I hit the function, notice that would actually be, and then go over, that'd be less than the actual area under that curve because the rectangle would stop short of where the curve is. So instead of doing that, we're going to keep this theme of trying to overestimate the area for a second here. And for this last rectangle, I'm going to let its left side boundary, the one we've actually already used for the third interval, be the height of this last fourth rectangle. So I'm going to go from the left side straight over and then back down to B to get my last rectangle. Alright, so if we look at our picture now, we have this curve cruising through the first quadrant. We have A and B as our left and right boundaries of some interval. And then we've created 4 rectangles that are kind of trying to represent the area underneath the curve. Of course, these are all over-representations, as we discussed, because there are parts of each of these rectangles that actually go above the curve, which is supposed to be the upper boundary of this region. All right, so we're going too high with these estimates. Now here's a fair question. That's all done with these blue rectangles. Let's go back now and try to use a different set of rectangles. I'll do them in red, if you can distinguish those. And this second set of rectangles, I would like to make an underestimate. So let's go through each interval, create a new rectangle. So the base of each these rectangles will still be the same things as the original ones here, where the width is the width of each of these intervals below. But this time, to make an underestimate, so like in this first rectangle, from A to the first little tick mark here, instead of using the right boundary of that interval, which went up as high as we could here and then went over as an overestimate, now let's use the left boundary. So from A, I'll go straight up until I hit the function, stop there, and then go over to make a rectangle, and then finish going down for that first interval. So now the estimate for the area is actually too low because I have all kinds of space below the curve that's actually not included with the rectangle. If we do the same thing for the first 3 intervals, we'll have 3 rectangles all rising until either the first of either side, so the left or the right boundary, hits the function, and when either one hits it first, we stop there and make a rectangle of that height. These would all be underestimates, again, because they all stop below the curve. Now this fourth interval, this last one, is a little different because in this case, I'm actually now going to use the right side of that interval to hit the function's graph and then move over. Of course, this will maintain an underestimate and stay underneath the curve, but I'm using the right side, kind of like for the overestimate rectangles, we had to use the left boundary on that last interval there. Now, for the sake of our further discussion, I'm going to add a couple more little notations to this picture. We already have our x-axis with A and B on it. What we want to do is describe the width of one of these intervals that we've put on here. Remember, we have 1, 2, 3, 4 different intervals. They're just kind of random width here at this point, but I'm going to describe the actual width of any one of those intervals as the value delta x. So delta x is just a variable. Of course, delta is a Greek letter. This has been a kind of notation we've seen already in calculus. But that width of any interval, I'm just going to call delta x for now. Okay, we'll get more specific with that in a second. And then I'm going to also pick I'll just move on to the next interval, the next rectangle, some value, some x value within the interval. And I'm going to call that x value just kind of anywhere floating in between the boundaries of one interval, one rectangle. I'm going to call that x value there x sub I star. Okay, so there'll be more on what that means and why we need it in a second. I'm just kind of getting the notation in the context of the picture here. So I put x sub I star in the third rectangle. there's no reason for that. It could be the fourth or second or third. I'm just trying to keep the picture as, clear and organized. I've already used the second interval to label this delta x, so I'm just kind of moving along for the next label, but they could be both in the same interval. It doesn't matter. The point is delta x is the width of one of these rectangles, and x sub I star is an x value that is somewhere within the base of some rectangle. Now, to build further on this kind of notation, the whole x sub I thing is meant to reference an index. So x sub I is the index. That could be labeled such that, the first rectangle is where I equals 1, the second rectangle is where I equals 2, third one is where I equals 3, and so on. Now, this is just a convenient labeling scheme. So each interval is labeled by I, and there are 4 of them, so we have 1, 2, 3, 4. That's just a common way of trying to label things of a sequential order in this way. Now, getting back to what we were doing with these estimates, let's get a couple definitions in here. First of all, as we've already mentioned, the first set of rectangles we drew, which were the blue ones, those are the upper area approximations. We already discussed those are all too big, right? There's extra space above the curve in each of those blue rectangles. They're too big. So that would be an upper approximation of the area. In other words, it's the sum of the overestimated rectangles' areas. Overestimated because they went above the curve. Of course, now after that, in red we drew these lower area approximations, which are the sum of the underestimated rectangles' areas. And we already discussed that there's extra space below the curve. In other words, those red rectangles, the second set of them, are too low. They're all below the curve, so there's a little error in that they're too small. So we're either too big or too small with what we've drawn so far. But given that, let's also note here that if I could find a place in between the upper and the lower estimates, that must be where the actual area would be, right? These are approximations. One's too big, one's too small, so the actual must be somewhere in between them. And for now, we just want to understand and note that. Now, let's keep going with this idea. To improve approximations, increase the number of rectangles. And for convenience, we can use the following. Now, before we get into all this notation, let's think about what that would mean to increase the number of rectangles. Every estimate rectangle we drew in this previous picture, whether it was an overestimate or an underestimate, showed the error by the space by which the rectangle was too high in the case of these blue ones or too low in the case of these red ones. And so we've kind of shaded in all the error that this approximation produced here. But if I increased the number of rectangles, I could cut down on that error. So, for example, you could take one interval, I'll just pick the first one. If I were to cut it, let's say, in half, then I could draw maybe 2 overestimated rectangle areas in that first interval and end up with less error. I would still have some, but the overestimated error would be less than the original overestimate because I've made more rectangles that can do a better job accounting for the error, but it's not a perfect job by any means. So let's keep that in mind. Now, for convenience, we can use the following. Do you remember delta x labeled in our picture above? Well, that was the width of the interval, and it turns out that there isn't only one way to try to define the width of the intervals that you're using for the bases of these rectangles, but for convenience, we can let delta x simply be b minus a over n for n uniform width rectangles. So b minus a is the length of this interval, and then chopping it into n intervals would mean you're just cutting it into n intervals of the same width. It just turns out to be convenient in that way. Also, secondly, let's let x sub I star, remember that was the x value we just put in the middle of one of our intervals. Well, it turns out that it doesn't really matter where that value is, as you'll see in a moment how we're going to use it. So for convenience, we're just going to use the right boundary of the ith interval. And that right boundary is defined by a plus I times delta x. And so this is just a convenient way to set up the algebra. It turns out that the place we use in any given interval for this x sub I star value doesn't matter. Now, it's also going to turn out that that x sub I star value is what we're going to use to compute the height of a rectangle. So in the estimates, we were using either the right side or the left side of each rectangle, as we just discussed. In some cases, the right side was the overestimate, and in some cases, the right side was the underestimate. It just depended on the rectangle and what the curve was doing there. But the function value at x sub I star is going to end up being what we use for the height of a rectangle. So x sub I star in some cases in our picture was the right side, in some cases the left side. We're just going to say that for convenience, it doesn't actually matter in the end with our calculation where it is in the interval, so we're just going to call it the right boundary because it's the simplest algebraic calculation. Now, with that being the case, note that we can compute the area of the ith rectangle as follows. F of x sub I star would be the height of the rectangle, and then delta x would be like the base, or you could say the width and the length, right? The point is, in our picture, I'm just going to draw another simpler copy of it. In our picture, we had some interval, and then x sub I star is going to be some x value within that interval. Could be in the middle of it, could be left or right sides of it, doesn't really matter. But the point is, when you say f of that value, that's going to give you some kind of height, and we're going to use that height to make a rectangle. And of course, the base of that rectangle is the delta x. The height is f of x sub I star, which means in even a simpler picture, which I'll draw now further to the right, we just have a rectangle whose base is delta x and whose height is f of x sub I star. So base times height is how we compute area of a rectangle, and that's how those measures are done in this picture we've set up. So f of x sub I star times delta x is really just a base times height calculation, which is really just the area of a rectangle. Base times height. That's it. Simple geometry here. Now, to use some other more familiar math notation, we can summarize our definition as follows. The approximate area under a continuous curve, has to be continuous, can be defined as A equals, A for area equals, and now we're using the sigma notation, remember that means a sum, from I equals 1 to n of f of x sub I star times delta x. Wait a minute, we just saw that. That's how we defined the area of one of these rectangles. So what I'm saying is, if you take the area of one rectangle, which of course is delta x times f of x sub I star, that's just base times height, but you do that with every rectangle that's used to approximate something. So if we go way back up to our original picture, we had 4 rectangles in this picture estimating the area. They were either too high or too low. But the point is, if I were to add the area of, let's say, all the red rectangles, which were all underestimates, or all the blue rectangles, which were all overestimates, that would be my approximation of the area under the curve in that region. Now, the actual area could be found. Remember we said that this approximation could be improved if we just simply increase the number of rectangles, because you create less error when you increase it. Well, what if we had, instead of 4 rectangles above, maybe 8, or 8,000, or 8 million, or 8 billion, or, wait a minute, what if we do this calculation, but let n, the number of rectangles, go on to infinity? Well, that's about as close as you can get to an exact area. In fact, when you let it go to infinity, which of course we can only do with a limit, that ends up producing the actual area, only possible by this limit, because that's the only way we can let n go on to infinity. You can't draw an infinite number of rectangles or intervals, or you can't even imagine it, or even a computer couldn't do an infinite number of them. So this really transcends the technology here, this concept with the limit. But it turns out that the actual area under a continuous curve bound by certain regions can be computed as follows. A equals the limit as n approaches infinity of this same area approximation sigma sum notation. The sum from I equals 1 to n of f of x sub I star times delta x. Again, this is just a base times height calculation. It looks all fancy with the math notation, but it's really nothing more than a base times height. And when you add up the base times height area of all the rectangles you're using to approximate it, but you let the number of rectangles, denoted by n, go on to infinity, you're reducing it to theoretically zero error, which will give you the actual area under the curve. Now, speaking of area, there's another application that can be used with this same concept and even the same notation, and that is distance. So you may recall that distance is modeled by or computed by this formula, distance equals rate times time. Well, since rate times time is the same kind of calculation we would use as like a base times height or a length times width of a rectangle, distance can also be computed just like area can under a curve, as we just saw previously, and we treat it just the same way like area. So it's just really another application of the same concept, and you can use the same kind of calculation for the limit, as we just saw here, where instead of finding the actual area, you could possibly find the actual distance covered. Let's try an example where we want to set up, but do not compute or evaluate yet. Okay, we're not quite there yet, but let's set up the limit used to find the actual area under the curve given as f of x equals x squared plus the square root of the quantity 1 plus 2x, that's all under the root, for the boundary of x being greater than or equal to 4, but less than or equal to 7. Alright, so now this function, x squared plus the square root of 1 plus 2x, is a little more complex than a simple polynomial. If you go way back up to the original picture we drew, I just drew a nice simple curve here, y equals f of x. This is oversimplifying the scenario, but it's sufficient for understanding the concept. In reality, you could have any crazy function that's at least continuous, and so in this case we have this f of x equals x squared plus square root of 1 plus 2x, but we're stuck between 4 and 7. Okay, so that'd be like the a and b in the example listed above. We want to set up the limit used to find the actual area under this curve bound by x equals 4 and x equals 7. Now, this can be done given what we just defined above for the actual area. We said above a equals the limit as n approaches infinity of the sum from I equals 1 to n. Remember, I is the index. That's kind of telling us how many rectangles or intervals we have. And then what came after the sum, what we're adding up, is simply the area of the rectangle. Remember, it was f of x sub I star times delta x. Now, this specific notation of f of x sub I star, that's not used by every textbook author. Some authors use it, some don't, some use maybe a simpler looking version. The whole point is, remember, x sub I star is just some place in the ith interval from which we compute the height of the rectangle. So specifically, f of x sub I star, remember that's just the height, and delta x is just the base, or you could say the width of the rectangle. So remember, this is just a base times height calculation, which is really just the area of a rectangle, but we're doing this area of a rectangle for n rectangles, and we're doing it while n goes to infinity. Okay, so this is part of the definition above to compute the actual area. Now, this is just the formula copied down. We want to plug in this formula as it relates to this problem, which gives us more specific information. So let's start by computing the key pieces of this formula, which specifically would involve delta x And as you'll remember above, we defined these for convenience to say, you know what, if we just let delta x be b minus a over n, that's just splitting the boundaries from a to b up into n equal width or uniform width intervals. And in this specific problem now, b and a are the boundaries of the interval from 4 to 7. So that would be like 7 minus 4 over n. In other words, we could say delta x is really just 3 over n. Okay, so let's keep that in mind. That's going to be our delta x. Furthermore, as we defined above, we're going to let x sub I star, remember we said for convenience, we're going to let that be just the right side of each interval. Well, we defined that as a plus I delta x above generally. So in this specific case, remember a is 4, so that's going to be 4 plus I times delta x, which we've already defined as 3 over n. Okay, so we have our delta x and we have our x sub I star. So now let's put this all together to define our actual area given all the formulas we have above and now what we've designated for delta x and x sub I star. We know that area, the actual area, is the limit as n approaches infinity of the sum from I equals 1 to n of, as the formula said above, it's f of x sub I star. Well, given what f is above, we can actually be more specific with it. Remember, defined above, our function is x squared. Well, instead of x, we're going to use this x sub I star. So really that's 4 plus 3i over n. If I just kind of borrow this x sub I star value we already defined here, that's going in for my x, but it's squared for the first term in our function, x squared. Then it said plus the square root of 1 plus 2 times x sub I star, or just x. Well, I'm going to plug in then, so 1 plus 2 times 4 plus 3i over n, going in for the x in our function defined above. Notice I'm slightly simplifying the algebra of x sub I star. Instead of I times 3 over n, I'm just kind of writing it as 3i over n. Algebraically, it's the same thing. But this ultimately now, what we have in brackets here, is the f of x sub I star from our formula above. That's plugging in x sub I star to the f function defined above or given in this example, as we can now see. Now it looks kind of messy, but remember, we're not actually going to evaluate this at this point. We're just setting it up. Okay, well we're not done, because after f of x sub I star in our formula for this limit, as you'll know above, we also have to multiply by delta x. Well, delta x in this case is simply 3 over n. And so with that in place, we now have the formula all set, where we have the limit as n approaches infinity of the sum of f of x sub I star times delta x, and of course those are defined specifically to the function given and the boundaries given in this example. Let's try another example where this time it says use 4 rectangles to approximate the area upper and lower under the curve f of x equals sine of x from x equals 0 to x equals pi over 2. Alright, so let's get a visual going for this one. We'll just draw a basic quadrant 1 graph where we have an x-axis horizontally, an f of x-axis vertically, and we have the function and the specifications for how to set this up. We want 4 rectangles, and they give us the boundaries. From x equals 0, well that's the y-axis, to x equals pi over 2. So let's kind of just go down a little bit on the axis and throw down pi over 2. If those are the outermost boundaries, from 0 to that, and we want 4 rectangles, let's draw 4 rectangles of equal width by first cutting the 0 to pi over 2 in half. That gives us 2 intervals, but then let's cut each of those in half. So, of course, the first cut in half would give us pi over 4, but then if I cut those intervals in half, I would have pi over 8, pi over 4, 3 pi over 8, and then pi over 2 as my interval markings. Now, we know what generally actually we know exactly what the sine function is and behaves like in this context. We know that f of 0 is 0 because the sine of 0 is 0. So we'll put a solid point there. We also know that f of pi over 2, sine of pi over 2 is 1. So that would be like at the peak of the sine function. So we'll put a point up there as well. And then this would be where the function is just increasing in its sinusoidal curve toward that function. So we're not really worried about the scale of our drawing. We're just trying to get a fairly accurate estimate of how this goes. Now, in this case, we're trying to find the approximate area upper and lower for this curve. Now, notice that it's an increasing function over this interval, meaning it's from left to right, only going up. And if we are careful to estimate, we could try to get an upper estimate, as we saw initially way above in our notes, by using the right boundary of each interval to create a rectangle. And of course, this works with increasing functions because the right boundary of an increasing function over an interval will always be higher than the left boundary. So we could use right boundaries for this upper estimate of all these rectangles. We'll do that in this pink color. And notice then that the height of all these pink upper estimated rectangles, the height of these rectangles is going to be the function output at the right side of each interval. So like f of pi over 8 is the height of this first rectangle. F of pi over 4 is the height of the second rectangle. Okay, and so on. Now, that's good for the upper estimates. Let's understand then that the lower estimates would be, well, instead of using the right boundary of each interval, we're going to use the left boundary for an increasing function that will work for the underestimates, just like the right side would work for the overestimate. This is true for an increasing function. Of course, if it's decreasing, it's the opposite. And if it's increasing and decreasing, then you might have to switch which side of the interval you use, depending on where the interval is with the function. So in that case, the underestimates will be the left side boundaries making the rectangles. We'll notice then in the first interval, there actually is no height to the rectangle with a left side boundary because remember, f of 0 is 0 here. So there's 0 height to that rectangle, it's just flat. Okay, fine. Moving on to the next one, the left side boundary at pi over 8 would create a rectangle with that height, f of pi over 8. In the third interval, the left side boundary would be f of pi over 4. That would create a rectangle that's an underestimate. And in the last interval, the left side, f of 3 pi over 8, would create, again, an underestimating rectangle. Let's actually write out the calculations here to compute this. We want an upper estimate, which we've already kind of drawn out in the pink rectangles that are all above with an increasing function. That was all the right boundaries. The area of any given pink rectangle would be base times height given the dimensions we have. Well, base times height for the first pink rectangle would be its base, which is pi over 8, that's the width of the interval, times the height of it, which would be f of pi over 8. So that's just base times height of that first rectangle, which is the area of it. If I move on to the second rectangle, the base, well, the same width occurs for each rectangle, which is why we can call pi over 8 the base of any of them. And by the way, that happened conveniently because we knew we had 4 rectangles, and so we just started cutting stuff in half to get 4 equal width rectangles. And so pi over 8 is the base of all 4 of these rectangles. Of course, the height of the second rectangle, this pink one, was the right side boundary of it, so that would be f of pi over 4. Okay, the third rectangle, again, is pi over 8 for the base. The height for that one would be f of 3 pi over 8. And lastly, pi over 8 for the base times f of pi over 2. This calculation will give us our upper estimate as we've defined it in this picture. Now, we can approximate this. You can punch this all in a calculator. I did so and got 1.1835. Of course, make sure you are in radian mode on a calculator using the trigonometry here. But that's our upper estimate for the areas. Similarly, we can find a lower estimate by using the other corresponding boundaries for our lower estimated or turquoise color rectangles. In that case, it'd be for the first rectangle. Remember, that was the one that was just flat. There actually is no height to it. That's fine. We're still going to write out the calculation. That'd be the width of the interval, so pi over 8 times f of 0. That's where we know that's 0 already, so that's going to be pi over 8 times 0, which is nothing, but we're still writing it out. That's the first rectangle. The second one would be, again, pi over 8 for the width of it, but now if you go back up to the second turquoise rectangle, the underestimated one, that one had a height of the left boundary being used, which was f of pi over 8. The third rectangle area would be pi over 8 times f of pi over 4. And the last one would be pi over 8 times f of 3 pi over 8. So we're using a different set of values for inputs, notice, for the lower estimate, because those lower estimate rectangles are used by using the opposite sides of each interval when compared with the upper estimate. Again, we could compute this or roughly estimate it as 0.7908. That could be done in a calculator. Again, make sure you're in radian mode. But there now is our upper and lower estimates. Of course, you could compute the exact values of these if that was requested somehow. That's much more cumbersome at this point. It's fine to get the concept here and just give an estimated rounded decimal.